Hello students, welcome back again. In this part we will discuss about periodic motion, oscillatory motion, simple harmonic motion, their applications along with the mathematical expressions. In this part we will discuss about graphical analysis also involved in the simple harmonic motions. So let's start. Hello students, in this part we would like to discuss basic mechanical equations, mechanical system behind the oscillatory and periodic motion. The first part we would like to discuss what periodic motion is. Actually we must understand the difference between oscillating and periodic motion. Oscillating is actually to and from motion, and periodic is just that the motion that repeats after a certain time interval. Periodic can be to and fro, cannot be to and fro. We can see the examples under this. Means for this, a periodic motion is when the motion of any object continuously repeats itself. This can be repeatedly moving back and forth, or it could be moving in a circular orbit of rotation. We can say the example like there is a mass, there is an object that is oscillating in a fixed radius circle. It is due to the centripetal force, and A is the acceleration, that is radial acceleration, centripetal acceleration having value v square upon r or r into omega square, and v is the tangential velocity. We must know whether this is periodic motion or oscillatory. It is not oscillatory, but it is periodic motion. So periodic, it must have a constant time period. In case of oscillatory, it is just to and from motion. Like a case of simple pendulum, if it executes to and fro, means left extreme and then right extreme. At the extreme position, it has the maximum displacement called as amplitude, and at the mean position, its energy is maximum. So in this way, we can understand the difference between oscillatory and this. Example is what? That repeated moving back and forth. It is a part of periodic. If any motion in which it is back and forth, and a periodic, and in which acceleration is directly proportional to the negative of the displacement, that called SHM. So SHM is a part of periodic, right? So this. Now we would like to discuss second part. So what are the basic introductory factors involved in simple harmonic motion? So we can say a simple harmonic motion is a vibratory motion in a line between 2 points. We can see the case of if we have a spring connected with a block, it is on a system. We can say if x is equal to 0 over here. On giving some small fluctuations to the systems, it can go to, or means we can say extension produced in the system, that is equal to positive x, and compression involved in the system, that is equal to minus x. Actually, these are the maximum displacement. We are calling it as minus a, positive a. These are the amplitudes. It executes oscillation about the mean position, in which its acceleration is directly proportional to the negative of the displacement from a mean position. Why I am using the word negative? It is just due to the restoring force. So we must understand the topics involved. A simple harmonic motion is a vibratory motion in a line between 2 positions. Another example, a case of simple pendulum. Simple pendulum is just an arrangement. A bob is connected with a light massless rod that executes to and from motion about the mean position due to the restoring force. Third case, hydrometry system. If you place some liquid in a U-tube, and due to applying some pressure or force at one side, it executes harmonic situations at that time. So it is under simple harmonic motion. Second part, the speed at both the ends is 0, because at the extreme there is a static situation. Maximum potential energy take place, no involvement of kinetic energy, and we know that kinetic energy is just a function of velocity or motion. With no motion, no velocity, velocity is 0 at that position. So we can say kinetic is 0 at extreme and potential is maximum at extreme. It comes under simple harmonic motion. Now, motion is driven by elastic restoring force proportional to the displacement from the center. Means center is the mean position or equilibrium position where system would like to return or restore its energy. But we need to apply some external force to the system. Who is responsible? Which force is responsible to bring back system to the mean position? That is just the elastic restoring force. Examples can be simple pendulum. We know that in a simple pendulum, if there is a tangential force acts towards the center, that is mg sin theta. In case of spring, a spring force exerts towards the center, that is minus of kx. A case of hydrometric system, that is what? A dragging or thrust that brings the system to the mean position. So these are under simple harmonic motion, in which restoring force is directly proportional to the negative of the displacement. Now, acceleration being proportional to the force. Of course, we know that restoring force is equal to mass into restoring acceleration. Hence, it is always proportional to the displacement from center and always in the negative direction of the motion. Negative direction means the nature of the tendency of that force is just to oppose the displacement. If any system is at mean position, positive x, negative x. It means if there is a spring connected with a blow, extension produced on applying some external force, that due to that spring force, the system would like to regain or restore its energy to the mean position. And in that case, restoring force is directly proportional to the displacement both in opposite direction. Positive displacement both is positive x-axis, but spring force is acting towards negative x-axis. That's why they would be F equal to F is directly proportional to minus of kx. So we can say F restoring is always directly proportional to the negative of the displacement from the mean position. As we know that in case of simple pendulum, it is the mean position. Now after a certain time, it reaches over here, making some angle theta with the vertical. So what? In this case, there is a restoring torque, because we must understand the translational force and rotational force. Rotational force is actually the torque. So means we can say there is weight acting downward and mg sin theta is responsible to bring that system to the mean position. So we would like to calculate restoring torque, that is directly proportional to the negative of the angular displacement. And that restoring torque is mg sin theta into the length L, and that is equal to I into alpha. I into alpha, and that I is moment of inertia and alpha is the restoring acceleration, restoring angular acceleration. So we can say SHM, a linear SHM, or just a angular SHM. That we will discuss in the next slide. But we must know the condition for a system to be SHM means its restoring force must be directly proportional to the negative of displacement, or restoring torque must be directly proportional to the negative of the angular displacement from the mean position. If it is satisfied, then the system is SHM, otherwise not SHM, simple harmonic motion. In the next slide, we will discuss a particle undergoes a motion of uniform speed along a circle. Its projection on a particular diameter undergoes a simple harmonic motion. Means like that, if it is going in a circular, if it undergoes circular constant acceleration, it would have two acceleration. Restoring acceleration means AR and tangential acceleration AT, and the resultant acts at some position over here. So they are talking about if a particle undergoes a motion of uniform speed along a circle, its projection on a particular diameter undergoes a simple harmonic motion. So means we can say to and fro. Okay, to and then fro means it regains its diametric position. Like there is a point A and B. So what it repeats after a certain time interval, t by 2, then t by 2, then t by 2, then t by 2. So if any object is over here, means observer is placed at the center, with respect to that observer, we can say the system executes simple harmonic motion. But all this phenomena depends on frame of reference. Means if the system is at center, with respect to him, the system is SHM. But if a system is outside, we can say it is just oscillatory system. It is not oscillatory, it is just periodic motion. It would not be SHM then. So if we change the location of observer, the phenomena of system will be changed. Now in the next slide we will discuss, you can see a simple harmonic motion is defined as the periodic motion without loss of energy. Of course, energy can never be created nor destroyed, but it transfers from one form to another. We can say total mechanical energy remains constant. That is just sum of kinetic plus potential. Kinetic is associated with motion, potential is associated with position of any system. That changes with respect to the motion of the system. Now, in which the acceleration of a body is directly proportional to the displacement from the mean position and is directly towards the equilibrium. That's why we are getting A is directly proportional to negative of x. We can say initial condition of a spring at the mean position it is at rest when applying some external force means due to weight mg acting downward, weight just a force due to gravitation, it is equal to the restoring spring force, that is kx at equilibrium. It's not in a system still. We want to put the system in equilibrium. What we will do? We will apply some external force to the system. On applying some force, it will attain a maximum position vertically downward. And then spring would like to restore its situation, its energy, its force. That's why its restoring force will be directly proportional to the displacement from the mean position, and we can depict the graph. Negative amplitude over here. We can say maximum amplitude, minimum amplitude, and it is the one complete time revolution from mean to positive extreme, mean left extreme, and then mean. So we can say a complete time revolution is required for one operating just to operate simple harmonic motion. In the next graph, we can, in next situation, we can say spring block system. There is a block of mass m that is connected with two springs, and we can say it is just a parallel system. When a block is connected with two springs, whether they are same side or the spring are in opposite side, but the system is a parallel system. Now, we would like to say this execute to and from motion above the mean position. So we can say this is just the mean position, we can say at the junction part. So what? Compression, expansion, compression, expansion. Expansion in one spring along with compression in another spring. It means potential energy drop in one system is equal to potential energy in the second system. And in between that, redistribution of kinetic energy takes place. So we can say small displacement x from its equilibrium position sets up a restoring force m, which is proportional to x acting in a direction towards the equilibrium position, in which f is equal to minus of x, where it is just due to the Hooke's law of elasticity. Hooke's stated that whenever we are applying a force, external force to a system, a spring system, the restoring force means the force due to a spring is directly proportional to the negative of the displacement, and just to remove that proportional sign, we will put Hooke's constant, and that is characteristics function of the spring quality. Now, negative sign imparts here the mean of restoring force is in opposite direction to the displacement in the system, we can see. So here we can say a spring force changes, means green sign is the spring force and blue sign is the expansion reduced in the system. Always they are in opposite direction. So this law is proved. Now, kinematics of SSHM. Uniform circular motion can be translated into linear SHM and obtain a sinusoidal curve for displacement. We can see here, if the system is at rest at t equal to 0, t equal to 0 at point P, we applied some force to the system to give it some expansion, to give it some extension, to provide it some motion. But due to restoring phenomena, it would like to return to the mean position. So what? Okay, fine. What we did then, at a moment we analyze the motion of a system at any time between P m to n, like that. We got there is some angular displacement in the system. There is some angular displacement in the system. That angular displacement is actually theta, and that is equal to angular velocity into time t. Angular velocity into time t. So we want to say that displacement at that time can be denoted by the letter x. So what we want to know, a is the radius, it is just the maximum displacement similarly over here. So we are getting sine of theta is equal to x by a, and we are getting x is equal to a sine of theta, and we can say x is equal to a of sine. Angular displacement is just a function of angular velocity into time t. Of course, we can see here. So x is just the displacement at any time t, and that is equal to a of sine omega into time t, where omega is the angular frequency, t is the time, x is the displacement at any time t, and a is the maximum displacement. We called it as maximum displacement. It is just a sinusoidal curve, so we would like to draft it on a graph where at t equal to 0, we will get amplitude or displacement is 0. At time increases, displacement changes from 0 to maximum. So what? We know that sin theta is maximum at 90 degree. That's why we got sin 90 is equal to 1. It means at 90 degree amplitude A is equal to the maximum displacement. And in this way we define the graph. We can also depict this graph on the basis of cos operator. So cos theta is equal to y by a or maybe x by a. It depends. Now proceeding to the main situation, we can say at time t is equal to 0, the object is at point M, mean position, and after time t it moves to the point N. Therefore, the expression for displacement is given as x is equal to a sin theta, where theta 1 is equal to 0, theta plus phi. So actually, when we want to discuss the standard equation of a simple harmonic motion, we can say the general equation can be represented y equal to or x is equal to a sin omega t plus theta. X is the displacement at any time t, a is the maximum displacement that called as amplitude, sin is the operator, trigonometric operator, angular frequency is just the frequency to complete one revolution in time t. T is the time at t is the instant time at which we want to know the location of or want to measure the displacement. And what? Phi is the initial phase change. That tells actually what was the phase, means at what time, whether it is lagging or leading or started from 0 phase. It can be either 0, it can be positive theta, it can be minus theta. If it is leading, we will put plus theta. If it is lagging, minus theta. Actually, it is just a comparative phenomena that tells the initial situation, initial location of the trigonometric equation, trigonometric operator or equation of SHM. And we call phase. Phase is omega t plus phi. Now, we can see here the graph of the system, like a particle executes simple harmonic motion in which the phase changes with respect to time t. At time t equal to 0, amplitude is 0 or maximum displacement is 0. At time t, where angle pi by 2 is, so there is a maximum displacement. At pi it is minus 1, and at another theta it is 3 pi by 2, and the last it is 2 pi. So here we discuss graph for one complete revolution. We found that its amplitude is getting decreased or increases. So means at x is equal to 0, its amplitude is 0. At t equal to, means we know that as theta is equal to 90 degree or pi by 2, we can say omega t is equal to this, so we can calculate the time. So means at t equal to t by 4, at t equal to t by 4, because we just divide complete time period into 4 segments: 0 to t by 2, t by 2 to t, 0 to t by 4, t by 4 to t by 2, t by 2 to 3t by 4, and then 3t by 4 to t. So we got amplitude is maximum at two locations, positive A, negative A. That's why we can draft. And as I told you, redistribution of energy take place in this phenomena. So it is just sum of kinetic plus potential. And that means we can say spring is connected with a block that execute as a jump, in which energy is just sum of kinetic plus potential. So kinetic minimize, potential maximize. Potential minimize, kinetic maximize. So these are the phenomena under SHM. So what we have, because SHM considers simple harmonic motion. So we must know harmonic motion. One more thing I would like to add here in this segment, that we are talking about simple harmonic motion. If its restoring acceleration is directly proportional to x to the power n, it is just a condition of harmonic. It is just a condition of a system to be harmonic, because in harmonic progression series we can discuss if x is equal to 1, means degree of the displacement is 1, we can say restoring acceleration is directly proportional to minus x to the power 1. So this is a case of simple harmonic motion. If x is equal to 2, we can say it is double harmonic. If x is equal to 3, we can say triharmonic. Means it changes phase 3 times in one complete evolution. So these are the case under the kinematics of SHM. We would like to switch to the example. In this example, we are given a system execute simple harmonic motion whose displacement x varies with respect to time t according to the relation x is equal to 5 sine 2 pi t minus delta. X is in centimeter, t in second, but we have to find. In part A, we have to find amplitude. So easily we can compare this equation y or x is equal to a sine 2 pi into frequency into time t minus plus minus that is 5. So on comparing we are getting x is in time, x is in centimeter, t in time, we have to find amplitude. On comparing we are getting x amplitude a is equal to 5 centimeter. Period, they are talking about complete time period. So we know that omega is given here as 2 pi. So that omega is actually 2 pi by t. So on comparing we are getting t is equal to 1 second. So that is equal to, period is equal to 1 second. We want to know frequency. So we know that frequency is actually 1 by capital T. So that is equal to 1 by 1, that is equal to 1 hour over here in the graph. And now we are getting phase constant of the equation. So phase is actually equal to minus pi by 2. So it is a case of lagging. So means we can say its graph can be as it is lagging. So sine theta minus pi by 2. So if it is it is sine omega t, and if it is lagging, so we can say its graph is like this. So means it is already over here. So means we can say that it's just a phase. Already we can say x is equal to a sine theta minus plus minus sine inverse the value of amplitude given, whether it is positive or negative. If it is given as negative, we will put it minus theta because a case of lagging. If it is given positive, then we will put positive sine inverse the value of amplitude, and it is a case of leading. Second part, the velocity and acceleration of object at any time t. So we will know this relationship after in the next slide, but I would like to tell you velocity. So velocity can be calculated on differentiating the function, that is dx by dt. So on differentiating we are getting that is 5 into cos of 2 pi t minus pi by 2 into 2 pi into 2 pi. So what we are getting, that is, it is just a equation of velocity and acceleration can be calculated on differentiating this dv by dt. So in this way we will get that is minus of again 5 into 2 into that is 4 pi square into sine of 2 pi t minus pi by 2. So means actually we know that the phase of acceleration is always opposite to the displacement, but some constant word is used, is admitted. That's why negative sign. Negative 5 into 4 to the power 4 into pi to the power square 2. Now the displacement, velocity and acceleration of object at t equal to 2 seconds. So what means, we are placing time t equal to 2 seconds, we will get 4 pi means. So in this the third part we will know a or acceleration is equal to a or 5 into sine 2 pi into 2 minus pi by 2. So we know that when we are getting 4 pi minus pi by 2, we will get different equation for different values for displacement, velocity and acceleration. So we will write the equation according to that, and simply the maximum speed and maximum acceleration. So we know that maximum speed is there at the mean position, that is equal to v equal to amplitude into omega, and acceleration is equal to minus of omega square into e. Okay, so on substituting v equal to a omega, so a is given as 5, omega is given as 2 pi, so the value is 10 pi radian per second. In case of, that is meter per second in case of velocity. In case of acceleration, that is equal to omega square into a. So on substituting the values omega and value of a, we will get the final answer. So in this question, what we did actually, we are given equation that is in the form of x is equal to a sine omega t minus pi by 2. Already from the graph we can see it is lagging. Now the displacement x is given in centimeter, time is given in second. In the part 1, they are talking about amplitude, frequency, period and phase constant. So if we know the standard equation, we just compare it x is equal to a sine omega t minus theta. So x is equal to 5, omega is 2 pi, so we can say omega is actually 2 pi per second, radian per second, and frequency is in hertz, that is inverse of time, reciprocal of time, and the phase relationship in that is minus pi by 2, means it is a case of lagging. Part 2, the velocity and acceleration at time t. So we will differentiate the given equation with respect to time t. We will get two equation for velocity and acceleration. In the part 3, they are talking about displacement, velocity and acceleration at time t equal to 2 seconds. So in case of displacement, we will put the value of t equal to 2 seconds in the main equation. That will become x is equal to 5 sine 4 pi minus pi by 2. So 4 pi minus pi by 2, that is equal to 7 pi by 2, and we will put the graph according to this. Also the case of velocity, we will differentiate it and then put the value of t is equal to 2 seconds. In the third part, they are talking about acceleration. Again, we will differentiate the velocity relationship and substituting the value of t equal to 2 seconds in the main equation. Of we will get the answer. Part D, maximum speed and maximum acceleration. So maximum speed is there at the mean position where displacement becomes 0, and the value is v equal to a into omega. A is amplitude, omega is already calculated from the main equation. Maximum acceleration a is equal to minus of omega square into a. Okay, so always we know that when the displacement is maximum, acceleration is minimum, and vice versa. So that is minus of omega square into a. We will put the corresponding values and we'll get the answer. This question is just a formula based question. So in this part, we discussed about kinematics involved in the simple harmonic motion, periodic motions. I hope you understood the topic.